Hi, this is Mr. Mack. This is a video about trigonometric functions and right triangles. So let's start out with the basics. First of all, if you have a right triangle, that means that your triangle has a right angle. And ordinarily what we do is if we have a right triangle, we look at one of the angles that is not a right angle, and we will label it with some variable. Now, in trigonometry, a lot of times the convention is to use Greek letters, and so we're going to take a look at this right triangle and the angle theta. Now, theta is the angle that's marked here. And what we're going to do is we're going to define each of the sides of the right triangle in terms of their relationship to theta. Now, I hope you can see that the side that the arrow is pointing to right now is the side that is opposite the angle theta. So this is called the opposite side. Now, the side of the triangle that is one of the two line segments that makes up the angle is referred to as the adjacent side. So the side of the triangle that is not the hypotenuse is that makes up the angle is called the adjacent side. And then of course the side that is the hypotenuse we call the hypotenuse. So many times we'll just say the opposite, the adjacent, and the hypotenuse. Now, trigonometric ratios have been defined based upon right triangles, an angle, and these names for the sides. Now, the trigonometric functions are sine, cosine, tangent, and then cotangent, secant, and cosecant. Now, each one of these functions has a three-letter abbreviation. I probably should have given myself a little bit more room here. Let's move this over this way. Now, the abbreviation for the sine is SIN. The abbreviation for the cosine is COS. The abbreviation for the tangent is TAN. The abbreviation for the cotangent is COT. The abbreviation for the secant is SEC. And the abbreviation for the cosecant is CSC. Now, ordinarily, what we would do is we would define the ratio of two sides of the triangle with respect to an angle. So the sine of theta is going to be defined to be the opposite side over the hypotenuse. The cosine of theta is defined to be the adjacent over the hypotenuse, and the tangent of theta is defined to be the length of the opposite side over the adjacent side. Now, the cotangent of theta is the ratio of the adjacent to the opposite. The secant of theta is the ratio of the hypotenuse to the adjacent side, and the cosecant of theta is defined to be the hypotenuse, the ratio of the hypotenuse to the opposite side. Now, if you'll notice here that the cosecant of theta is the reciprocal of the sine of theta and vice versa. The cosine of theta and the secant of theta are reciprocals, and the tangent of theta and the cotangent of theta are also reciprocals of one another. So we have 6 functions there, and they're all defined in terms of signs, in terms of opposite and adjacent. Now, at this particular point, I would be remiss if I didn't tell you of the memory device M-N-E-M-O, mnemonic. Let's see, N-M, mnemonic. I think this is the way it's spelled. It's a memory device. And the memory device is, as legend has it, the name of a Native American chief, Chief SOH CAH TOA. Now, SOH CAH TOA is something, you know, when you talk trigonometry to high school students, they will say, oh yeah, SOH CAH TOA. SOH CAH TOA means the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. SOH CAH TOA. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. And then you need to remember which trigonometric functions are the reciprocals, but SOH CAH TOA will do the whole job for you then. Now, notice that these functions are written in such a way that we are taking the sine of an angle or the cosine of an angle or the tangent of an angle. This is kind of, again, like functional notation. So if we took the sine of 19 degrees, for example, that would be the ratio of the opposite to the hypotenuse in a right triangle with an angle of 19 degrees. In fact, let's just go ahead and do one of those and talk about this for a minute. See, let's say, for example, we have a right triangle with 19 degrees right here and a right angle here, and we want to know the sine of 19 degrees. Now, at this particular point, we're going to pull up our calculator, and the scientific calculators do this. Also, let's just check to make sure that we're in degree mode. See, now I press the mode button, and I'm going to go down here. Do you see where it says radian? I'm going to go over and press enter on degree, and then second quit. Now, my calculator is in degree mode. You need to have your calculator in degree mode when we're dealing with degree measured angles. So if I type sine and then 19 and close parentheses, the calculator is going to give me 0.325, let's just say 0.3256. Okay, now what that means is the ratio of the opposite side to the hypotenuse in this right triangle is 0.3256. Well, now here's a question for you. Think about this for a minute. What if the triangle were actually a different size? Let's let it still be a right triangle with a 19-degree angle, but then we've got different lengths for our sides. Isn't this going to change? Well, if you think about it in geometry, it won't change because this green triangle that I have right here is similar to the bigger blue triangle, and so the ratio of corresponding sides are in proportion, or in other words, the ratio of corresponding sides is equal. So what that means is, in this triangle, the ratio of the opposite to the hypotenuse, since it's 19 degrees also here, is exactly the same as the ratio here. That's why it doesn't really matter what the sides of the lengths of the sides of the triangle are. If we know it's a right triangle, and if we know an angle, we know that all of the right triangles with that angle will be similar. And so if we do ratios of sides, that will be constant. That's why we can use the sine of an angle or the cosine of an angle or the tangent of an angle. Now, the real power in this is if we have a way to find these ratios for any given angle, then if we have some information, we can use this information to discover other things about our situation. And we'll do a little bit more on that later. But first of all, The next thing we need to do is we need to talk about special angles. Now, in your geometry class, if you had one, we talked about two special triangles. One was a 30, 60, 90 triangle, and the other was the 45, 45, 90 triangle. Now, sometimes this one, instead of being called 45, 45, 90, is called the isosceles, ISO, oh, gosh, ISOSCELES. I think that's isosceles right triangle. Anyway, these two triangles have some special relationships, and it enables us to know the actual values of some sines and cosines. So let's start with the 30, 60, 90 triangle. Now, the way we get a 30, 60, 90 triangle is we start with an equilateral triangle. Now, if you have an equilateral triangle, all sides being equal, let's just say S, 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 then all of the angles are 60 degrees. And if we were to split, if we were to bisect one of the angles, let's say, for example, we bisected this angle so that it came down through this side, it would meet at a right angle here, and this angle would be 30, this angle would be 60, and this would be 90. Now further, we know that this length right here is half the length of the whole side, and then we could use the Pythagorean theorem in the right triangle. S squared would be equal to 1/2 S squared plus, and I'll just call this H squared, and we could solve for H. And let's do that. We get S squared plus S squared over, no, I can do this. S squared equals S squared over 4 plus H squared. Now I'm going to have to subtract S squared over 4 from both sides. So I'm going to make this 4S squared over 4. That's the same thing as S squared, right? And so when I subtract S squared over 4, I get H squared is equal to 3S squared over 4. And so H is equal to the square root of 3 times the square root of S, which is S, over the square root of 4, which is 2. So this height here turns out to be square root 3 over 2S. Now, what that means is if you have a 30, 60, 90 triangle, and let's draw it this way now. Here's the right angle, here's the 30-degree angle, here's the 60-degree angle. If this is the hypotenuse, and let's let this be 2, then this side is the short leg, which is 1, and this leg is the square root of 3. Now, that means that the sine of 30 degrees is going to be 1 over 2. And the cosine of 30 degrees is going to be square root of 3 over 2, because it's adjacent over hypotenuse. And the tangent of 30 degrees is going to be 1 over the square root of 3. Now, we don't often, but you could rationalize this and make it square root of 3 over 3. It's probably a good idea in this particular case to remember 1 over the square root of 3 better. Now, if we have a 30, 60, 90 triangle, but we're dealing with the 60-degree angle, then the hypotenuse is 2, this is 1, and this is square root of 3. Now it turns out that the sine of 30 degrees is square root 3 over 2, opposite over adjacent, 30, 60. What am I doing here? The sine of 60 degrees, because this angle is 60, is square root 3 over 2, opposite over hypotenuse. The cosine of 60 degrees is 1/2, and the tangent of 60 degrees is equal to the opposite over adjacent, or square root of 3. And so we're able to get the sine, cosine, and tangent relationships for triangles that have 30-degree angles and right triangles that have 60-degree angles. And these are values that you should memorize. Now, I mentioned there was another special triangle, and that was the 45-45-90, or isosceles right triangle. So let's take a look at that one for just a minute. Now, the way we get an isosceles right triangle is we start with a square. Now, remember, a square is a four-sided figure that has all sides equal, and the corners are all right angles. And so if we take a diagonal of the square, and let's let this length of the square be S, and this length of the square be S, then the hypotenuse of this triangle, oh, and by the way, if we cut this in half, notice this corner angle here is a 90-degree angle. And since this side is equal to this side, these two angles would have to be the same. And if we have 90 and two angles that are the same that add up to 180, they each have to be 45. That makes this a 45-90 right triangle. It's also isosceles right triangle, so that's where we get the two names. Now, to find S squared is equal, H. That's an H, not an S. Can't even read my own writing. H squared is going to be S squared plus S squared. Well, now S squared plus S squared is 2S squared. So if I take the square root of both sides, I get H is equal to the square root of 2 times S. So in a 45-45-90 triangle, we know that the hypotenuse is one of the legs times the square root of 2. Now that we have that, let's take a look at the sines, cosines, and tangents of 45 degrees. Now, if this is 1 and this is 1, this is going to be the square root of 2. So we get the sine of 45 degrees is equal to 1 over the square root of 2. The cosine of 45 degrees is equal to 1 over the square root of 2. And the tangent of 45 degrees is going to be 1 over 1, which is 1. Now, I must say in these cases, usually this is rationalized to square root 2 over 2. But again, these are values that you should commit to memory. So in other words, you should know just off the top of your head what the sine, cosine, and tangent are of 30 degrees, 45 degrees, and 60 degrees. Now, what good is this? Well, this can be used to measure lengths and find angles when those things aren't known. Let's see if we can't come up with a couple of simple examples, and you'll get a chance to do a lot more in your homework. Okay, so first of all, imagine we have a building, and we are standing 800 feet away from the building, and we look up at the top of the building, and we figure that we're looking up at an angle of 54 degrees, and we want to know how tall the building is. Well, this is 800 feet. Can you see that the tangent of 54 degrees is equal to the opposite, which is, let's call this H again, the height of the building, H over the adjacent 800. So in this equation, we can solve for H. H, if we multiply both sides by 800, we get H is equal to 800 times the tangent of 54 degrees. And so if you just take your calculator, since it's in degree mode, we can say 800 times tan 54, close the parentheses on the 10, and press enter, we get 1,101.1. So height is 1101.1 feet. Now, I got to tell you the truth. My data here is only in one significant figure, so pushing it to 1, 2, 3, 4, 5 significant figures would make any science teacher just scream. But anyway, this is how you would find an unknown length. Let's do one more of these. Let's imagine that you are constructing a radio antenna. Okay, and so you've got this tall radio antenna. Now you know this radio antenna is 200 feet tall. And you know that you're going to go out 100 feet and you're going to put an anchor here and then string a wire from the base up to the top. Now you want to know how long this wire needs to be. Okay, so once again, or well, that one's kind of silly because we could use the Pythagorean theorem. Let's say, um, oh, okay. Uh, let's say instead of 100 feet here, let's just say the um, the FCC, the Federal Communications Commission, says that the angle of the guy wire for your radio antenna has to be, let's say 72 degrees. Okay. So now the question is, how long should the wire be? And I guess question number 2 is, how far away from the base should you put the wire? So first of all, let's see how long the wire should be. If you look at this triangle, we've got the angle 72, and we have the opposite side, and we want to know the hypotenuse. Now, you're going to have to say which trigonometric function relates an angle with the opposite side and the hypotenuse. And you will say, it's the sine. So we know the sine of 72 degrees is going to be the opposite, 200, over the hypotenuse, which we've labeled as x. Now, to solve this equation, we could probably start by multiplying both sides by x, and we get x times sine 72, 72 degrees equals 200. But then to solve for x, we're going to divide both sides by the sine of 72 degrees. And so we get x is equal to 200 divide sine 72. Now we can do that on our calculator. 200 divide sine 72, close paren. And we get 210.3 feet would be how long the cable needed to be. Now, if we wanted to know how far away from the bottom of the antenna we need to anchor the cable, we can use trig to find that one as well. Now, I better use a different variable here. Let's call this y. Why not? Okay. So if we want to know what y is, realize that we now have 72, the angle. We have 200, the opposite side, and we want to know y, the adjacent side. Well, now we know that the tangent is the function that relates an angle to the side opposite and adjacent. So we can say tan 72 is equal to 200, the opposite, over y, the adjacent. And once again, we have the same situation where we have tan 72 is equal to 200 over y. Now, one of the things we could do here is just multiply both sides by y over tan 72. I could have done this last time, but I didn't the first time. So notice the y's will cancel on the right-hand side. We'll be left with 200 over tan 72. And on this side, the tan 72's will cancel and we'll be left with y. So now, if we just take our calculator and divide 200 by the tan of 72, 200 divide tan 72, it'll show us that 65 feet from the base of the antenna is where we would have to anchor the wire. Okay, those are a couple of simple examples of how trigonometric functions can be used to find missing sides. Now, the next thing the book wants to talk about is inverse trigonometric functions. Now, remember, for example, the sine of 19 degrees is equal to, I've forgotten what that was, so let's just go back and get it again. Sine 19 is 0.3256. So this function actually is 19 degrees, comma, 0.3256. When we give it a 19 it gives us 0.32, oh, it gives us 0.3256. Now, the inverse function is the function that would have the ordered pair 0.3256, comma 19. Now, ordinarily, what we would do is we would say, all right, sine inverse of 0.3256, and what the function should give us then is 19. So let's do that. If I press sine inverse, now that is second sine. Notice, don't put sine and then x to the -1. That's going to take the reciprocal rather than doing the inverse. The inverse function for the sine and the cosine and the tangent are the second functions on those buttons, and that's standard throughout the calculator industry. It's not the reciprocal, it's the inverse function. Okay, now I'm going to type in 0.3256. 0.3256. Now that's not going to give us exactly 19 because I didn't use all of the number, but it's going to give us something pretty close, 19.001. Now, sine inverse, you can read this, the angle whose sine is, and then 0.3256. So what we did was we got the angle whose sine is 0.3256. In other words, if we take the sine of that, we'll get, or if we take the sine of that angle, we'll get 0.3256. So the inverse functions can be used to find missing angles. Now, let's see if I can't give you an example of that. Okay, imagine that we have a map here, and this is north. Now we have a boat out on the water, and it travels 10 miles north, and then it travels 17 miles east. And the question is, what is the angle that the boat now makes with its original position? In other words, what is this theta right here? Okay, well now notice again, we've got an angle, and we've got the opposite side, and we've got the adjacent side. So the function that defines the situation is the tan of theta is equal to 17 over 10. So that means that theta is the tan inverse of 17 over 10. Or theta is the angle whose tangent is 17/10. So if we were to take the calculator now, and what we do is we type second tan, 17 divide 10, close paren, we get 59.5. So theta is 59.5 degrees approximately. And that shows us that. Now that is everything except the angles of elevation and angles of depression. We need to talk about those also. Imagine, if you will, that you're standing on the ground, looking up at an airplane flying in the sky. Okay, and as you look at the airplane, it's kind of flying this way. Okay, now we call the angle that you're looking up the angle of elevation. Now, imagine at the same time you've got this T-90 pilot up here in the plane, and he's flying this way, and he's looking down at you. Now, the angle that you make with the horizontal in the pilot's eyes is called the angle of depression. Now, the truth is that the angle of elevation and the angle of depression should be the same because the horizon for you and the horizon for the pilot in the plane are parallel lines, and the angle of elevation and the angle of depression are alternate interior angles cut by a transversal between two parallel lines. So the angle of depression and the angle of elevation are effectively the same angle. Now, the only time this would trip you up if you don't know which is when some teacher or test writer writes a question and says, what is the name of this angle, and points to this one here. And if you call that the angle of depression, they're going to mark it wrong, even though the angle of depression has the same measure. Okay, so you will need to know angle of depression and angle of elevation for that. But other than that, what you really need to know is that they are equal and they represent how far off the horizontal you are either one way or the other. And that, my dear students, is 13.1. We're done.